Hello, and welcome to Lecture 2 of Math 1B03. In today's lecture, we're going to learn about Gaussian elimination. This will be the first of two lectures on this material. If you're following along in your textbook, you should see section 1.2 of our textbook. So just a quick summary of what we saw last time. We were looking at systems of linear equations, and we saw that it was stated that any particular system of linear equation has either no solutions, it has exactly one solution, or it has an infinite number of solutions. And we divided these into various categories. So if you were above the line, you were called an inconsistent system. So inconsistent system. And if you fell into the other two categories, you were called a consistent system. So our goal today is to kind of figure out or start laying the groundwork in order to find a procedure to solve a system of linear equations. Now this procedure is called Gaussian elimination. So today what we're going to do is look more at the procedure or the algorithm which basically manipulates a matrix. And in next lecture, we're going to make the connection to systems of linear equations and use this method in order to figure out if our particular system of linear equations either has no solution, exactly one solution, or it has an infinite number of solutions. So the basic idea behind Gaussian elimination is what you want to do is manipulate the augmented matrix so it has a particular form. So in particular, what we want to do is start with any matrix and we want to somehow do some sort of operations on our matrix so that at the end of the day, we end up with something that looks like this. And I'll explain what these symbols are in a second. I'll just draw my matrix. So I've drawn a matrix, and each of the squares are going to denote a non-zero element. So this will be a non-zero element. The star, or the asterisk, can be any number. It can be either 0 or negative or a positive number. And then over here, we have to have zeros in the bottom left-hand corner. So if you look at this, what we have is kind of a staircase of zeros in the bottom left-hand corner. So we'll write it like that. We have a staircase of zeros. So what we're going to be doing is describing a procedure that allows us to start with any matrix and somehow put it into this particular form, so that in the bottom left-hand corner, we're going to have a bunch of zeros, and we will have certain entries of our matrix being non-zero. Okay. So in order to do this, we need some terminology to kind of describe the matrix that we're aiming for. So just going back a page here. So we want some terminology to kind of understand what this matrix has, or what shape this matrix has. So going to the next page here, there's a bunch of definitions. And so the definition actually carries on a bunch of pages, but we're going to start with the basic form here first, which is the notion of an echelon form. So a rectangular matrix is in echelon form if all of its non-zero rows are above any rows of all zeros. So that just means that our matrix, if you have a row of zeros, they all end up at the bottom of the matrix. Each leading entry, and so this is a term we'll use many times, which is going to be the leftmost non-zero entry is in a So if you're reading across a row, the first time you hit a non-zero entry, that's called the leading entry. And this leading entry is in a column to the right of the leading entry in the row above. So this is going to kind of contribute to the staircase shape. And then all entries in a column below leading entry are 0. So let me just give you an example of such a matrix. So 1, 2, -1, -3 in the first row, 0, 6, -6, and 3 in the second row, and 0, 0, 0, and 15 in the last row. So this would be considered echelon form. And we see that it's an echelon form. Well, first of all, condition 1 doesn't apply because there are no rows of zeros. If there had been a row of zeros, I would stick it at the bottom. Each leading entry, so let me underline each leading entry, the 1, the 6, and the 15, is in a column to the right of the entry in the row above. So here's my leading entry, and it's to the right of the 6. And the 6 is a leading entry, and it's to the right of the 1, which is the leading entry in the row above. And then all entries in a column below a leading entry. So all here, 1 is a leading entry, 6 is a leading entry, 15, and everything below that is a 0. Okay. Now there's actually more terminology that we may want to put on our matrix into this shape. The next terminology refines this. So a matrix is in row echelon form if each leading entry is a 1. So if we go back to my matrix up here, and we have a 1, a 6, and a -15, that's not going to be in row echelon form because I have a leading entry of a 6 and a leading entry of a 15. Neither of those are 1. However, I will give you an example of something that's in row echelon form. I will take the matrix 1, 2, -1, -3, 0, 1, -1, 1/2, and 0, 0, 0, 1. So this is in row echelon form. Okay. Now, we may even want to refine this even a little bit more. The next terminology that we use refines this notion further in the sense that we want the leading 1 to be the only non-zero entry in its particular column. So a matrix is in reduced row echelon form if number 5, okay, so this is my 5th condition, each leading 1 is the only non-zero entry in its column. Okay, so as an example of that, we could have something like 1, 0, 1, 0, 0, 1, -1, 0, and 0, 0, 0, and 1. The underlined entries are my leading entries, and they are the only entries in those particular columns that are non-zero, right? So this 1 here is the only non-leading entry here. Same with this guy over here and this guy over here. So this is in reduced row echelon form. And you'll notice that these examples have been picked such that the previous example fails to have the next property, right? So this guy here is not reduced row echelon form. And if we go back to this guy here, the first one, this guy is not in row echelon form. Okay. So the point of this definition, it's quite wordy, and there's 5 different things you have to keep in mind. But is important though for later on is because we want to be able to take any matrix and put it into one of these particular forms. And so this language here is going to be helpful when we come to the next part of today's lecture, when we try to use the Gaussian elimination to put our matrix into one of these 3 forms. So we will continue this into the next part of our lecture.